Welcome to a lesson with Dr. Powell. In this video, we will solve a related rates problem two different ways. This related rates problem is on a triangle where different side lengths and angles are changing. Here it looks like dc dt. So c is going to be this side length, and it looks like it's not changing. So this side length is constant. Also notice that there's an angle which is constant. The angles in this triangle are labeled as such. Beta will be opposite B, gamma will be opposite C, and alpha will be opposite A. So we know that beta and C are not changing, but A can change, maybe. We're trying to figure out how it's changing at a particular moment in time. So at a particular moment in time, we're going to assume that this side length B is changing at about 10.756 feet per second positively. So it's going to be growing instantaneously right then at this moment that fast. So perhaps if you waited 1 second, B would be quite a bit larger, at least instantaneously. That's what this information is telling us. Also, with that particular growth per second, it looks like alpha is going to be wildly growing. It's going to at 45.837 degrees more every second. So instantaneously, it's growing very fast. As B grows, alpha is growing, and gamma is actually decreasing. So beta is growing, gamma is, and over here, so gamma is being extended out this way, becoming a smaller angle, and alpha will actually be growing. Okay, so in this setup, instantaneously at this moment of consideration, the question is, how fast is side A changing? So we have a snapshot. At this particular moment in time, we're going to say, maybe we know this information. We know what all the angles are. We know what the side lengths are at this moment. So this is a particular moment in time, but just wait, things can be changing. So instantaneously, we have some information at this moment. We know the instantaneous rate of change of gamma, alpha, B, C, beta, and then we need to figure out what A would be. Now, here, this tells us that C and beta are constants, at least instantaneously constants at this moment, so we can treat them as such as we proceed. Okay, so what we need, first of all, is we need an equation that gives us a relationship between A and some of these other variables, where we know their derivative information. And then we take a derivative of that equation with respect to t, both sides, thinking of them as being functions of t, both sides. So the derivatives should be equal as well. And then after we get so this is going to be function equivalence. That's kind of important here. Function equivalence. So we're going to, thinking of A, B, and C, gamma, alpha, beta as being variables, and perhaps, variables, and then having one output of an expression like a function with multiple things coming into it. So we're going to be thinking of something function equivalence. But really, we're going to be thinking about every variable as being a function of t. So really, we're going to have a function of t being equal to a function of t. And from a function of equivalence, we can get, we can take a derivative of such an equivalence across an equal sign and get a derivative equivalence. And then only then, after we have a derivative equivalence, can we plug values in for A, B, C, gamma, beta, and gamma, beta, and alpha. And the reason being is, as soon as you plug something in, you've actually assumed something. You've assumed that something's constant. So when you take a derivative, it's going to be a little bit different than it would actually be if you assumed that they weren't. I mean, that's kind of a big thing right there. Also, yeah, so if you have an equation where you've restricted some value of a, b, and c, all of a sudden you've assumed that, or alpha, beta, gamma, you've assumed that those variables were constant, then taking a derivative, I mean, the derivative equivalence will assume that. So, you know, it might mess some things up here, especially when we want things to be variable. So, everything that doesn't have a rate of change of 0 will be variable. So we need to keep that in mind. Okay. However, we could potentially plug in the value of c and beta before we take a derivative, but we'll do it later, just kind of as we think about it. In fact, in this video, we may not plug it in necessarily at all. I just want to focus on getting the derivative equivalence so you can see how to solve for dA dt rather quickly, but I'll leave the details for the viewer on that specifically. It's not really hard. It's just going to be pretty simple to solve for it. So let's get going and see how this is going to work. All right, one simple way of doing this, assuming you don't really know, well, assuming that someone doesn't know the law of sines at all, or cosines or anything like that, we can still work through this pretty quickly. So A, if we think about it, I'm just going to draw a little line right here. So right angles. This side length will be of importance right here, because we can express it in two different ways, and that'll give us our function equivalence. So we can express it as, in particular, think of this A as being a hypotenuse. You can think of a triangle. This is kind of a favorite triangle here on the unit circle as a hypotenuse of 1. And then if this is an angle, in this particular case, say it's gamma, then this would be sine of gamma, and this would be cosine of gamma. And this triangle is similar to this one because they share two of angles that are the same, so all three angles are the same. And in particular, but this one is rather a 4. So just multiply all the sides by 4. Aha. So this is what we want. 4 sine gamma is another way of writing this line down, right? The length of that. So 4 sine gamma, but let's write it another way. Thinking of this triangle over here. Now, thinking of a right angle here, and let's go to alpha over there. So think alpha, and then there's a right angle. Now on the unit circle, the hypotenuse of 1, what would these side lengths be? Sine of alpha, cosine of alpha. But this hypotenuse is not a 1, it's a 5. So just multiply everything by 5. And look, 5 sine alpha. That's another way of expressing this length right here. So we have an equivalence. And in particular, it looks like, you see this 4 here for function equivalence. We were just talking about something. So maybe this is good that I mention this right now. This 4, we should rewrite as not 4, but what 4 is representing A. You don't want to plug in anything before you take a derivative. So I will make that correction, and I'll leave it in the video. And that's so that you can, to emphasize that we really want to keep everything as variables before we take a derivative. All right, so A sine gamma, okay, coming from here. Then over here, the same thing. See this 5? We want to think of it not as 5, but as being C. Now, it's true. I mean, C, we're going to assume to be a constant. So C. And so that'll help us when we're taking a derivative here, because we have dc dt is 0. Okay, it's not going to be changing at all. Okay, so a sine gamma is equal to c sine alpha. We have an equation that relates these variables together. Now we can take a derivative of both sides of the equation, thinking of a, gamma, c, and alpha as being functions of t. Albeit c, we're going to assume to be a constant function of t, at least instantaneously, in our derivative. So using that idea on this side, you can think of c as just simply being a constant times sine of alpha. What would that be? Using the chain rule, thinking of alpha as being a chunk, a function of, a t, let's think. Go back here. What's the derivative of sine? It's cosine. So c times cosine of alpha, but then with the chain rule you have to multiply by the derivative of the inside, which is d alpha dt. And look. Oh wait, but we can't plug in d alpha dt right now, because when we assume that the derivative of sine is cosine, we're assuming that we're in radian mode. So we're talking about, so this rate of change right here is actually going to be radians per unit time, which is seconds. So radians per second. So we will have to, before we plug in, we're going to have to convert this d alpha dt, d gamma dt. Beta dt is really easy. It's just going to be 0 radians per second. But for these guys right here, and notice they're just negatives of each other, which should make sense. Because the angles add up to 180, and this guy's a constant, so alpha plus gamma is going to be a constant value, and when you take a derivative of that, the derivatives will be negatives of each other, so that's great. So that's reflected here, but we'll have to convert this to radians per second. Okay, so how do we do that? How do you do the conversion? Let's just review that for a moment. So if you have degrees, right, what we're going to do is we're going to relate 180s to pi, because every pi is 180, right? So if you want to know, and usually when you write down radians, you like to think of fractions of pi. You can kind of think, okay, this is what fraction of pi? Well, you can get it by, like, in terms of radians, like the radian measure is what fraction of pi is. Well, it's the same thing as saying what fraction of 180 is this guy. So you can just simply say 45.837 over 180, and that's how many pies we're going to have. And so that's just another way of that's a simple way of converting, but please convert it before you plug in d alpha dt. But okay, so back to what we're doing, though. We just took a derivative of this side of the equation, assuming that c will be constant, at least instantaneously. Now, if you didn't want to do that, you could say c is variable. Now, so then this would be like multiplication of two functions, and both of t, like this would be c of t. And then you could use a product rule. So you could say dc dt times sine of alpha plus c cosine of alpha d alpha dt. And that would be fine as well. But notice that dc dt is 0, so we didn't have to do it at all to begin with. So we have c cosine alpha d alpha dt. On the other side, right here, we take a derivative, and here we're assuming that both a and gamma, see this, we're trying to figure out what d dt is, so we're going to assume it's variable, and alpha, they're variables, so we're going to be having to use a product rule here. So we'll end up getting d dt, derivative of a, times just sine of gamma, plus, now a being constant, times the derivative of sine of gamma, thinking of gamma as being a function of t, because these derivatives are with respect to t. So this would become cosine of gamma, but then you have to multiply by the derivative of the inside gamma, so d gamma dt. Notice how important the chain rule is. The chain rule is what brings out these guys right here, like, these rates of change. when we get our derivative equivalents, taking derivatives, we want to relate these guys together, these instantaneous rates of change. So now d alpha c, so we have dA dt as one of them, which was good. And notice that we have information. We know what d gamma dt is at this moment, and we know what d alpha dt is at this moment. We also know at this moment what c is. C is going to be 5, so now we can plug in. We can start plugging things in now, okay? After we have had a function equivalence, which was right here at this step. This was our function equivalence. And then next, after we get our derivative equivalence and we've used the chain rule to get these things coming out, now we can start plugging stuff in and we can solve for dA dt. Notice it'll be pretty simple to solve for dA dt because we have information about everything else to plug in. And so this will be a number on this side. I'm just going, for brevity, let's just say we have something like this. dA dt times just a number, let's just call it capital A, plus another number, call it capital B, is equal to a number, call it capital C. Pretty easy to solve for dA dt now, right? Because we know A, B, and C are, and then we can just solve it. This is a linear equation, if you will, if in dA dt, where dA dt is a variable, or at least what we're solving for, and then these other guys are constants. Not too hard. You could plug things in and solve that. I'll leave that for the viewer. One little note before we move on, or before we end the video, I guess. What if we started out right here, and there are many different ways we can actually come up with our original function equivalence. I came up with one that was rather simple. I'll just give you an example of something else, which is not too bad, but probably not my first choice. However, not bad. So what we could do is start by thinking of a bigger right triangle like this. Okay, so the right angle is here. So you kind of in our minds imagine a bigger right triangle coming all the way here, here, and so forth. And this angle right here is beta. This angle right here is gamma, then alpha. And we'll think of this as pi minus beta. Now instantaneously we're going to assume beta, pi minus beta are constants, and c right here is also a constant. I'll just relabel it again for that length. Okay, so what we could do is we could quickly see that this part of this triangle right here is actually c. So see that's like the hypotenuse times the cosine of that angle. Now, if you need to have a little thought on that, I guess you could think of a triangle in the unit circle with the 1 as the hypotenuse length. And then you would have, if your angle was pi minus b, beta, what we have sine pi minus beta and cosine of pi minus beta. But wait, okay, let's multiply, the hypotenuse is c, so let's multiply everything by c. Yep. So c times cosine of beta of pi minus beta would be that length. Okay. So let's just erase the rest of that right there. Okay. So using a similar idea, actually we saw in that little picture that this length right here from here, right here is actually c times the sine of pi minus beta. Now, this is nice because we have a relationship on a right triangle with the sides. We know this bottom side, right down here, is a plus c cosine of pi minus beta. All right, and we know that this side length right here is c sine pi minus beta. And Pythagorean theorem, this side squared plus this side squared is equal to that side squared. Okay. Okay, so square the sides and set that equal to b squared. Okay, this would be like our function equivalence equation. Now, great. It wasn't as simple as our last function equivalence equation, which we had right here. A sine gamma is equal to c times sine of alpha. But notice we didn't use anything other than just triangles, knowing where sine and cosine were on them with respect to a hypotenuse, and the Pythagorean theorem. Really, that's all we used. Not too hard. You could have gotten something similar to this if you knew something about law of cosines. That's fine, but you really don't need it. It can all be done in such a way. So you get a function equivalence right here, remembering all the variables are functions of t. But now when you take a derivative, you can remember a few things. C and beta are constants. In particular, this whole bit right here is a constant. And actually, see this c and sine of, because of the beta is a constant and c is a constant. And similarly, right here, this part is actually a constant. So in taking a derivative, it's great for the derivative equivalence. This part, whole part is gone because it's a derivative of constant. Then it's just right here. The derivative is just use power rule, a plus a constant squared. So it's just going to be like 2a plus this constant. I'll just write it down. C cosine pi minus beta. So power rule, but then times the derivative of the inside. Derivative of the inside, this part's constant, so it's just a, right? d dt. So you have like, so then, okay, so you have something times d dt is equal to, on this side, thinking of b as being a function, so we have to use the chain rule. It's a chunk here, so with the power rule, so 2b, but then trade-off, since b is not t, taking a derivative with respect to t, we multiply by the derivative of b, db dt. So this equation's pretty simple to solve once you plug things in. Now we can start plugging in after we get this derivative equivalence equation. So we can plug in what the particular values are for at this moment in time for A, for B, and looks, I guess it's just A for C, for beta, and for B. You plug those in, and pretty much on this side, this is just going to be like some number times d ADT, and we're trying to find d ADT. Okay. And then at this moment in time, we actually know what dBdt is. That's great. Times it, so that's going to be like equal to another number, like this is a number times b when we plug in what b is, which is 8 times 2. So you're going to, so this is a very simple thing to solve. I'm just letting b represent that whole side because after you plug in, it's just going to get a number, right? And I mean, we know what dBdt is. We don't know d ADT, so I will let that be variable right here. But we have a constant something times d ADT is equal to another constant, and then d ADT simply in this case would be what this b is in this particular here divided by a, and then we're done. So not too hard. I mean, take it or leave it. That way wasn't bad either. Coming up with the other one seemed a little bit more straightforward, but here in this one, after taking derivatives and just realizing what was constant, and how do we know it was constant? Because of these zeros right here, right, for their derivatives. The derivative is equal to 0. At least instantaneously it's a constant. Maybe if the time changes, won't be, but that's okay. Instantaneously, you can assume it's a constant in the derivative here because we're focusing at one particular moment in time. That simplifies the process a little bit here. So just at the moment when here. So we're not solving for what d ADT is as a function. We're solving for a particular value or output of d ADT as a function of time. at a particular moment. So we're solving for a particular number, a particular output value, not a function. If we were solving for a function, then even though these things say 0 and 0, if we're thinking of them as being instantaneous, we would not be able to do this. We could not assume that's a constant. We would not be able to assume that was a constant. We'd have to assume everything was variable if we wanted to really get d/dt as a function. Okay, I hope you can glean something from that. This is a little practice, especially on a triangle with related rates. Thanks for watching.